Integration is a powerful mathematical tool with numerous real-life applications across various fields. Here are some key examples. Physics and engineering. Kinematics, calculating the position, velocity, and acceleration of objects. Electromagnetism, determining the electric and magnetic fields. Structural engineering, analyzing forces and moments in structures. Economics and finance. Consumer and producer surplus, calculating the area under demand and supply curves. Continuous compounding, determining the future value of investments. Biology and medicine. Population dynamics, modeling population growth and decay. Pharmacokinetics, understanding drug concentration over time in the body. Environmental science. Pollution modeling, estimating the spread and impact of pollutants. Resource management, calculating sustainable yields of natural resources. Computer graphics. Rendering, calculating the area and volume of objects for realistic images. Animation, determining the motion paths of objects. Statistics. Probability distributions, finding probabilities for continuous random variables. Regression analysis, estimating relationships between variables. Astronomy. Orbital mechanics, calculating the trajectories of celestial bodies. Light intensity, measuring the brightness of stars and galaxies. Everyday applications. Travel, calculating distances and fuel consumption. Architecture, designing curves and surfaces in buildings. Integration helps us understand and model the world around us by summing up small parts to find a whole. Do any of these applications particularly interest you? Sure. Let's break it down. Integration. Integration is a fundamental concept in calculus that involves finding the integral of a function. Essentially, it helps us calculate the area under a curve. This process is the reverse of differentiation. Integration can be used to sum up small parts to find a whole, which is particularly useful in various real-life applications. Calculating distances and fuel consumption. When it comes to calculating distances and fuel consumption, integration plays a crucial role. Here's how. Calculating distance. To calculate the distance traveled by a vehicle, you can use the integral of the velocity function over a given time period. If you have a velocity function, vt, the distance s traveled from time t_1 to t_2 is given by. This integral sums up all the small distances covered over each tiny interval of time to give the total distance traveled. Calculating fuel consumption. Fuel consumption can be calculated by integrating the fuel consumption rate over the distance traveled. If you know the fuel consumption rate Fx, e.g. liters per kilometer, the total fuel consumed F over a distance from x_1 to x_2 is. For practical purposes, you can use a simpler formula if you have the total distance traveled and the total fuel used. The fuel consumption rate can be calculated as. For example, if a vehicle uses 50 liters of fuel to travel 600 kilometers, the fuel consumption rate is. This can also be expressed in liters per 100 kilometers by multiplying by 100. Practical example. Imagine you want to plan a road trip and estimate how much fuel you'll need. If your car's fuel consumption rate is 8.33 liters per 100 kilometers and you plan to travel 500 kilometers, you can calculate the total fuel needed as. This way, you can budget for your trip and ensure you have enough fuel for the journey. Does this help clarify how integration is used in calculating distances and fuel consumption? If you have any more questions or need further examples, feel free to ask. Derivatives have a wide range of applications in various fields. Here are some key examples. 1. Physics and engineering. Motion analysis. Derivatives help determine velocity and acceleration from position time functions. Electric circuits. Calculating the rate of change of current and voltage. Structural analysis. Understanding stress and strain in materials. 2. Economics and finance. Marginal analysis. Determining marginal cost, revenue, and profit. Structural analysis is a crucial aspect of engineering that involves determining the effects of loads on physical structures and their components. Here are some key points about structural analysis. What is structural analysis? Structural analysis is the process of calculating and determining the effects of loads and internal forces on a structure, building, or object. It ensures that structures can withstand the loads and forces they encounter during their lifespan. Key components of structural analysis. Loads. Dead loads, permanent static forces such as the weight of the structure itself. Live loads, temporary or dynamic forces such as people, furniture, and vehicles. Environmental loads, forces due to natural phenomena like wind, earthquakes, and snow. Structural elements. Beams, horizontal members that support loads. Columns, vertical members that carry compressive loads. Trusses, frameworks consisting of triangular units. Frames, rigid structures composed of beams and columns. Analysis methods. Equilibrium, ensuring that the sum of forces and moments in a structure is zero. Compatibility, ensuring that deformations in the structure are consistent. Superposition, analyzing complex loads by breaking them into simpler parts. Work energy methods, using principles of energy conservation to analyze structures. Applications of structural analysis. Building design, ensuring buildings can support their own weight and external loads. Bridge engineering, designing bridges to withstand traffic loads and environmental forces. Aircraft and ship design, ensuring the structural integrity of aircraft and ships under various loads. Mechanical systems, analyzing the structural components of machinery and equipment. Example, bridge design. In bridge design, structural analysis helps engineers determine the size and material of each component to ensure the bridge can safely carry vehicles and withstand environmental forces like wind and earthquakes. Engineers use mathematical models to simulate the loads and stresses on the bridge, ensuring it meets safety and performance standards. Importance of structural analysis. Structural analysis is essential for safety, preventing structural failures that could lead to accidents. Efficiency, optimizing the use of materials to reduce costs. Durability, ensuring structures can withstand long-term use and environmental